Okay. Now, I've got a system which is going to consist of this rotating beam and this beam, which is right above it. Okay, and these things are grooved. So if I could time this just right, I could drop this beam onto this one at just the right moment, and then there'd be two beams rotating, right? Okay. Now, what do you think would happen? Well, use a little thought. You got to see that. Well, this one's going to start moving. It's originally stationary at zero angular velocity, but this one's going to slow down. Okay, now physically, why is it that this one slows down and this one speeds up? Well, it's easiest to see why this one speeds up. If I drop this just right, so that, you know, now I have two beams, okay? And this one speeds up, something has to speed it up. What is it that speeds up angular velocity, angular motion? Okay. What do you need in order to speed up angular motion? Well, one answer, and it's a good answer, was energy. Okay. But we're not going to talk about the energy because it's going to turn out that the total energy of this two beam system is going to be the same. Well, no, it's going to change. Okay. But you're not going to be able to predict how it changes without understanding how the momentum changes, the angular momentum. Okay, it's the angular momentum you want to look at. Now, to get to that, just ask the question of what is it that speeds up that second beam? Well, you can say, yeah, it's the first beam. Well, yeah, but just what's the physical mechanism? What do you know about angular motion that tells you how something speeds up? And that's kind of vague, but think on it a little bit. Let's think for a minute about what you have to do to speed up any object. I got a bowling ball here and I want to speed it up. I've got to apply a force, right? What I have to do to speed up a rotating object? Well, I mean, I got an immediate response. Well, you got to apply a torque. Why don't I just say I got to apply a force? Well, then I say what force? You say, well, that depends on where it's applied. Because a force applied out here, a 2 Newton force applied out here is going to have a different effect than a 2 Newton force applied out here. Now, you come down to the conclusion that it's the torque. Okay? So the torque is what speeds up the initially stationary beam. So you got stationary beam, and you got a rotating beam rotating about some axis. Okay. You combine the two. Put the second beam to the first. Second beam speeds up. Okay. Now, when I say join it, I mean join it in an isolated system. So there's nothing exerting any force on these beams. We're going to say friction's negligible, which it pretty much is over short term. So we're going to join these two beams with no force coming from outside. just the force between the two beams. Now I'm going to drop the second beam onto the first, hopefully from a small distance, so we don't have a lot of vibration and stuff. So there are going to be forces in the vertical direction. The second beam's got to be brought to rest in the vertical direction. It's going to get some rotation, but in the vertical direction, it's going to come to rest. So the first beam is going to have to exert an upward force to stop at an upward impulse to bring the velocity, the vertical velocity, to zero. That's not going to affect the rotation if it's done right. Okay. Now, that's force. First beam drops from the second. Each beam has to exert a force on the other to stop the second beam, and then by Newton's third law, if the first beam exerts an impulse on the second beam, first beam exerts a force on the second beam exerts an equal and opposite force on the first, right? And that's the vertical motion. No rotation in the vertical direction. No rotation associated with the vertical motion. The rotation vector is actually vertical, so what I said before, right? Okay. As far as the rotational motion is concerned, what is it that speeds up the second beam? Well, you said it. Speeds up due to the torque on it, not the torque on it, by the rotating beam, okay? Okay, so at every point of contact, there are forces between the two beams. The force exerted at every point by the second beam, but by the rotating beam on the first, is equal and opposite to the torque exerted by the first on the second. Okay? Forces are all equal and opposite. I'll just say it's the same distance from the axis. So the torques are equal and opposite. Now, that whole argument is necessary to completely understand what's going on here. At the level of trust, you can say, well, okay, the forces have to be equal and opposite. The torques have to be equal and opposite. Again, it's because all the forces are equal and opposite and exerted at the same distance. The force of the particle 10 centimeters from the axis on the rotating beam are equal and opposite to the forces on the added beam, the second beam, at the same distance, because that's where both forces are exerted. Okay. Torques are equal and opposite, except equal and opposite torques. Well, angular momentum, I believe your text uses the letter L for angular momentum. It's moment of inertia times the angular velocity, okay? totally analogous to P equals mv. K is momentum. Okay. So we call this angular momentum, analogous to linear momentum. Analog is delta T equals F net delta T. You know, I ought to put a little bar over this. F net bar meaning average net force, because the net force is going to vary during that time delta T. And you don't need to worry too much about why, or about how, but you should worry a little bit about it. It's just, you're integrating the actual force as a function of time times delta T. Up here, it's totally analogous. Torque is analogous to force. Delta T is delta T. So this is angular impulse. This is impulse. This is angular impulse. Again, I'm not making a precise statement here. If you read the book, it's a precise statement, but I'll comment to make it a little more precise. But anyhow, angular impulses in a isolated system are all equal and opposite. That makes sense? Because if your system just consists of two objects, these two objects, it's pretty obvious. Well, anytime two rotating objects interact, they interact by equal and opposite torques. Again, assuming you have an isolated system. Okay, angular impulse, equal and opposite. The delta L is zero for the entire system, even though that's angular momentum, even though in this case, each of these experiences a change in angular momentum. Their total change in angular momentum has to be zero. Okay, so let's solve a problem. Okay, two typical beams of slightly different densities or thicknesses or whatever, so they don't have the same angular momentum. Omega 1 is 4 radians per second. That's first beam's rotating at 4 radians per second, about like this. Okay, maybe a little slower for that. Second beam is stationary. Okay. The objects join up. What's the common final angular velocity? Now, implicitly, the angular velocities are parallel. So maybe I ought to say these are parallel. Of course, with zero angular velocity, it really isn't parallel to anything because it doesn't have any. But the beams are going to be parallel, so the angular velocities are going to both have the same direction. So what's the common final angular velocity? The total change in angular momentum is 0. Okay. This tells you I'll leave the arrows off because everything's in the same plane, basically. Here's your total momentum, angular momentum before collision. Here's your total angular momentum after collision. Now, rather than plug numbers in at the very first, and there is some advantage in plugging numbers in, seeing what the quantities are. How about just solving this for omega f and then plugging the numbers in? Okay, now, you know, I just suspect that people are looking up and down at the board too many times to just be concentrating on solving this equation. Okay, we don't have time to write down everything necessarily and digest everything unless you write fast. But you could go to the video. You could do screenshots of every board and have them for yourself in 10 minutes. Okay, put them someplace where you can access them. Or copy them down at that point. Don't spend class time copying stuff down unless you think it's really helpful to your learning process, more helpful to your learning process than solving this equation and looking back and see what you have. So that's where we want to go. Still, it's really easy to solve the equation. Now, instead of I total, I wrote I1 plus I2. This is a system of just two objects. Right there we have it. Okay. And I1 omega 1, 0.06, that's 4.24. Okay, well, it's written kind of small, but it's obvious what the numbers are. You plug the numbers in. That's going to be 0.24 kilogram meters squared per second plus 0 kilogram meters squared per second. Mental velocity and I2 divided now by the total moment of inertia, which gives you It's not kilogram meter squared. It's about to write out all the units. I have to divide that by kilogram meter squared, right? And I get omega F is 2.4 reciprocal seconds. There's a radian in there. Radian is basically a displacement along an arc divided by a radius, which is unitless. Okay. And if you then insert your distance along the arc divided by the radius, you get radians. Okay. And you want to think about that. Okay. Anyhow, does that make sense? Now, if you go, this is at 4 radians per second, this is at 0, right? This has got more moment of inertia than this. It's got 50% more moment of inertia than this one. Which one is going to change velocity the most? Well, velocity of the second one goes from 0 to 0.24. And it should be 2.4. It is 0 to 2.4 radians per second, right? And the first is going to go from 4 down to 2.4. Well, the second is going to speed up by 2.4 radians per second. The first is going to slow down by 1.6 radians per second. What's the ratio of 2.4 to 1.6? It's 1.5. What's the ratio of 0.4 to 0.6? What's the reciprocal of 1.5? It's 2/3. Okay. So this is going to increase its angular velocity by 3/2 as much as this one decreases, because this one is 2/3 the moment of inertia of this one. And that's something you really want to have a feel for, those proportions and those numbers. People are not very good typically at this point in thinking in terms of proportions, but that's what everything really is in many cases. Okay, so you want to kind of focus on that and think about it. In any case, you understand this is very simple. It's a very simple equation. Okay. Now, if I had this is what I want to. If these things were rotating like so, I see the two magnets, and when I get close enough, those magnets are going to repel each other, right? That would be an elastic collision, in which case the kinetic energy would be conserved. Okay. This is an inelastic collision within objects joined together. If you paid attention to what some of the text is telling you that I haven't really talked about, but it's very simple. To calculate the total angular kinetic energy of the two beings rotating at 22.4 radians per second, it's going to be less than that of this thing rotating at 4 radians per second. But it's very simple. Just compare mv squared. You don't even have to worry about the 1/2. You compare mv squared before to mv squared after, you're going to have the same comparison you have between 1/2 mv squared before and 1/2 mv squared after, right? So we're not going to worry about the 1/2. What's mv squared? I omega squared. Okay. Well, here omega squared is 16. 16 times 0.06 is 0.96. So there you have 0.96 mv squared. Half of that would be your kinetic energy, 0.48 joules. Okay. So let's go with the 0.96 and compare that with what we have here. 2.4 squared is 5.76. You multiply that by 1, or by 0.1, okay, you get 0.576 as opposed to 0.96. So you just leave the I omega squared for this and this. If you want to take half, well, instead of 0.96 and 0.576, you'd have 0.48 and 0.2875, I think. Okay? Does that make sense? I wasn't quite right about that 75, something else, pretty close to that. So you have quite a bit more kinetic energy before than you do after. So I'm going to just say a note. Kinetic energy ain't conserved. You can check that out yourself. I did it, but you ought to write it out for yourself to reinforce it because you don't remember what you hear unless you've written it out and processed. At least you don't remember it as well. Some people lock it in as soon as they hear it. They could never forget it in the rest of their life. Okay? And you'll see some of those people when you go into an engineering program at Virginia Tech. Okay? Don't try to compete with them, just try to learn something. Okay? And you might even be one of them. You might have that kind of memory. Don't compete with them, but try to learn to work with them. Okay. As cooperative work is much more powerful. Okay. Now, does that kind of give you an idea about angular momentum? In the case of an elastic collision, like the two magnets repelling, those are conservative forces. When the things are approaching, magnetic forces exert exactly the same force at a given position as when they're repelling. So they do equal and opposite work. So the total energy, the net work done by those conservative forces is zero. So the kinetic energy has to be conserved. Okay. If the kinetic energy is conserved, then their relative velocity before equals their relative velocity after. Again, on this inelastic, you lose a lot of kinetic energy. Okay. If the two are rotating in opposite directions with just the right angular velocities, you drop the one onto the other and everything stops right there. Okay. So you lose all your kinetic energy. And that's just like a head-on collision between two cars of equal mass, where they lock bumpers or their engines join together or whatever. Okay. You don't want to be in those cars, but they'll come to a dead stop. All the kinetic energy goes into heat. Well, some of it goes into sound because it's a pretty good crash, but by far the bulk of it will go into heat. As we'll understand when we're studying heat. Okay, do you have a question, comment? You know, I'm not sure what that gesture means. Okay, hang on, let's get the comment. Okay, so we got into a discussion about, well, when you have the car collision, you get sparks and sometimes that'll ignite the fuel and then you get all kinds of energy transitions. Well, that fuel is kind of external to the mass of the thing, and it's kind of something you would then regard as external to the system of the two masses. Okay, and then all bets are off. Okay. Of course, the spark comes from friction of pressing engine parts, okay, which achieve some kind of charge separation. You also have electrical stuff going on in the engine that can cause sparks. So that's away from what we're doing. Now, I will make a note. Elastic means change in collision is zero. This implies by some argument that we might have time to do, maybe not, that the initial omega-2 minus the initial omega-1 is the negative of omega-2 minus omega-1 out, which is totally analogous to the condition that you have for an elastic collision in one dimension. It embodies, you're not going to be able to read it, but I said it. Okay. If you want me to write it down coherently after class, I will. If you want me to put it in the notes, put it on the website, just tell me. I'll make a note and I'll do that. Relative velocities after collision, relative velocity of the one beam relative to the other for collision is equal to the relative velocity after. Equal and opposite to the relative velocity after. So if you're riding one beam and you see the other one coming at you at a certain speed, and after collision, you see it going away at the same speed. Okay. Or if you're riding a car, a bumper car that has perfectly elastic properties, you see one car coming at you at some speed and going away from you at the same speed. That's key to analyzing a completely elastic collision. You could do it by setting momentum after equals momentum before, kinetic energy after equals kinetic energy before. You'd end up with some moderately ugly equations that you should be able to handle. Okay. But they reduce down to momentum before equals momentum after, relative velocity before equals is equal and opposite to relative velocity after. Okay, that's all I'm going to say about that. That's kind of take those words and take them back to what you're doing. You're still working chapter 9. Okay. That's the topic of chapter 10. Okay. Or is it chapter 11? I don't know, chapter 9 is momentum. I think it's 11. 9 is momentum, right? And 8 was potential energy. Okay. Okay. Another topic is gravitation. Now, as I said before, you can kind of think of at least an analogy to gravitation. Let's say you've got a magnet at the axis of this beam. And let's say the beam is non-magnetic. I want to keep it magnetic so the magnet doesn't fall off. So I don't want to use a meter stick. Plus meter stick's too long for the string. Okay. Now, this is a magnet and you have a steel ball out here. Then the magnet's going to attract that steel ball. Right? Remember, this isn't, let's say this is an aluminum beam here, so it doesn't have any magnetic properties. So you're just dealing with the magnet and the ball. As this thing rotates then, you can rotate it at such a speed you're not going to go back and forth. You can rotate it at such an angular velocity that the centripetal force required to hold this thing in the resulting circle is equal to the force that pulled the magnet. Okay? Now, that would be very tricky because the magnet doesn't exert an inverse square force. And I've mentioned the one problem that I encountered in Panofsky and Phillips' book on electromagnetism, which I worked all the problems. It's only one problem I couldn't solve. Neither could my professor. Said, if you had anything other than an inverse square force, like force was not proportional to 1 over r squared, but to 1 over r squared minus epsilon, where epsilon is as small as you want to make it, then you could not have stable orbits. Now, that would not have been the case with Panofsky and Phillips. They were doing the analogy with particles. You couldn't have stable atomic orbitals according to the Bohr model, which is totally equivalent. Now, really what's going on is not the Bohr model, but that's as much as you're going to understand at this point. Okay. Comes down to eigenvalues and eigenvectors in quantum mechanics. Okay. So make sure you remember about eigenvalues and eigenvectors if you're ever going to get into that aspect of engineering. All right. Comments aside, ball, magnet, orbit. Okay, that's an analogy to satellite orbiting a planet. Okay, if you move the magnet or the ball in closer, you're going to have more force. Okay, so your v squared over r is going to have to be a lot greater, right? So you're going to have to move this thing a whole lot faster. Your r is smaller. Okay, the v squared over r has to get bigger. So v has to get bigger. Okay, just intuitively, try to understand that statement. Also check out, make sure it's correct. Okay. So if you've got a mass, big M here, and a much smaller mass, little m, in the distance, center is r. Okay. Then you're going to have a force of attraction. Going to be toward the center. Get that arrow right. Understand it's back toward the center. Centripetal force, right? If it's a potential centripetal force. If you give this thing just the right speed, then the centripetal force it needs to maintain a circular orbit will be equal to this force. Okay. Now the neat thing about gravitation is this force is inversely proportional to the square of this distance. It's an inverse square force. How many of you have heard the term inverse square force in your education? Most of you haven't. Terrible, terrible, terrible indictment of our educational system. Even in middle school physical science courses, if they don't tell you that, they're doing you a terrible disservice because now you got to digest it and use it. And you haven't been thinking about it for 10 years, 5 years, whatever. Okay? It's totally new to me. So now you got to pull it out of pre-calculus, which nobody understands very well, because pre-calculus is taught so that people who will never understand it get through it. Okay? So you have those things that you got to process, which makes it that much more difficult to learn this stuff. But you guys are smart. You can do it. It's going to take you a little more time. And it's going to sink in more slowly. They don't would if you immediately said, oh, that's what they meant by that inverse square force. I've been thinking about that, wasn't sure. Okay. How much time did you spend thinking about the essence of compound interest before you got to pre-calculus course? Did you even see the essence of compound interest in pre-calculus course? How are you ever going to understand exponential functions? Okay. You know, I don't want to talk about the good old days, but of course I was educated during the prime years of the space race. But even before the space race, people were learning that stuff. People were seeing those things. Okay. You ever get a chance to influence the direction of K through 12 education? First place, make sure you know what you're talking about. Second place, just do what I'm telling you to do. Okay. No, make sure I know what I'm talking about. I say that just because you're going to have to process it now. Okay. And it's not something that your synapses have been conditioned to understand. Fortunately, it's not that hard. And your synapses have a lot of other connections that are going to be very helpful. Okay. What is? I'm just going to say it. I'm not going to tell you what an inverse square is. I'm not going to talk about inverse square proportionality. I got to leave that to you because we can't spend time developing stuff that you should have started developing after your education. Okay. But you can develop it. So I'm just pointing out this is something you need to understand. And if this is not an inverse square force, this orbit is not going to be stable. It's going to be like a pencil bouncing at its end. Okay. And if you try to synchronize out there in intergalactic space somewhere or in free fall, you can just climb a tall building, jump off through apparatus, and make sure your parachute's going to work. And you have a few seconds of free fall in which to actually investigate this. Okay. It won't be enough. So get up to the space station where you can really go. Okay. Get to work in your vertical leap. Okay. What I'm saying is, if this wasn't a perfect inverse square force, you wouldn't be able to maintain the circular orbit any better than you could have balanced against one example. At least little deviation, at least little disturbance. Throw this out of kilter to where the whole thing would never happen. So it all be atoms. Okay. I haven't worked that out at the quantum mechanical level. That'd be pretty. I'd be a little over my current head. I'd have to spend a year doing more quantum mechanics before I could think about it comparatively. Okay. The magnet is not an inverse square force. You wouldn't be able to do it with the magnet. Even if you could synchronize the rotation of the magnet to as finely tune it as you wish. Okay. You would never be able to tune it finely enough to exert the constant force it needs to exert and to recover from any little deviation. With an inverse square force, you can. Okay, that's good stuff. It's worth thinking about, but let's move on and see what you can do with it. Okay. Give it just enough velocity perpendicular to the R vector. You can't do this with a steel little m and a rotating magnet instead of him. Even if it's a rotating electromagnet that's rotating at almost exactly the right speed, you can never get exact. Even with feedback loops and all that kind of stuff, you can't modulate magnetic field enough to maintain a stable moment. Okay? You can't make it constant enough to maintain a stable moment. Because at the very least, for quantum mechanical uncertainties in position and so forth, it'll cause this thing to go all out of kilter. Okay? Kind of akin to trying to control the plasma in a fusion reactor with magnets. Okay? That's the hang up. That's why we don't have fusion. We kind of have it. They're able to maintain half decent fusion for a little while, but it costs too much right now. It's too unstable. You don't get enough energy. And you don't exceed the energy you put into it by enough for the energy you get out of it to be worth it. Okay? Except as a research. That's the big engineering problem. That's not a physics problem. Physics tells you exactly what you need. Well, maybe I'm overstating it, but it's an engineering problem. Okay? One that's kind of fascinating more. Okay. Well, enough about magnets versus gravity. This is gravitation. Okay. And I'm going to make this orange a vector. But then I'm not going to mention the vector has to recover it for a while. Okay. Your question. The distance 2r, what's going to happen to the required v relative to the distance r? So what can you tell me happens at distance 2r? What's the first thing that you can tell me we know about the distance 2r? Okay, so I pose the question, what's different at distance 2r? Now, I'm asking you, what's going to happen to v, right? You don't even think about that. First thing you think about is, what do we know at distance r, and how's that going to change? Once you can answer that question, then it's going to be fairly easy to figure out what happens to v. Now, what are two things that are going to change? Force is going to change, and the velocity is going to change, right? You don't have a handle on what's going to happen to the velocity, but you should know enough about what's going to happen to the force. Well, the first thing I told you I got is, well, the force is going to be less out there. Well, by analogy with a steel ball, imagine there's a steel ball and a magnet. Yeah, you know the further you get away, the less force, right? Okay. Well, gravity is analogous. The force falls off differently for gravity than it does for a magnet. Okay. For reasons that we won't understand until around March, even April. Okay. If distance 2r, what's going to happen? Okay, you're going to get less force. How much less? Let me pause. Okay, pose a question. I immediately got that. Well, half. That's a good guess. Okay. But if you keep in mind that the force, as I stated, is an inverse square, and if you had been exposed to that idea when you should have, and thought a little bit about proportionality, which you should have, but by the time you were 15, okay? Not your fault. It's the fault of design of the curriculum, which has some advantages, but I think there's too much theoretical education schoolism in it. Okay. Education schools are not totally bad. They do some good research, but sometimes think they extrapolate more than they should. Okay. On the other hand, there are all kinds of other reasons for the curriculum. So you guys fix it. I'm too old. Okay, now, yeah, nobody's going to listen to me. They might listen to you. Okay, so distance 2r, what's going to have the required be? I said it's an inverse square force. So 2 times the distance implies 1 over 2 squared equals 1/4. To the force. Okay. So b squared overall, but 1/4 is great. Okay. Now we're going to let v be the required v. We're going to let v be this force. And let's just call it let v naught be the original velocity, r naught the original distance. Then implicitly v1 and r1 are going to be the velocity and distance. Okay, well, we could write an equation like v squared over r is 1/4 v naught squared over r naught squared. Okay, we call that v1 maybe and r1. And something's wrong with that. Wrong with my equation. This comes out not making any sense. You're going to get just with 1/4 here. It's going to cancel 1/4. We're going to get v naught equals v1. Something can tell you. See if you can fix that. I want to move on to something else. Okay. There's going to be a ratio that kind of reveals something like Kepler's laws we haven't even talked about. And we haven't even talked about the law of universal gravitation, except in hand waving. Wait. Now, the problems I asked in the new set, I'll give you some background. Okay. And you shouldn't, I don't think you ought to necessarily read the chapter before you try to do the problems, because then you're going to be searching for equations to answer questions you can answer by understanding. Okay. And if you can't answer a question, it's a good time to just email me, somebody find me. Okay. Makes sense? And you ought to be thinking about it starting today, even if it's only for 10 minutes. All right, now, that's one thing. The new problems talk about angular momentum. They talk about orbital. Well, they talk about gravitation. Okay. And then they're going to talk about simple harmonic motion. Talk a little bit about simple harmonic motion. Okay, first thing you have to understand about simple harmonic motion of a particle is that the net force is negative kx. Okay. Also, torque being analogous to force and theta being analogous to position. You also have this equation, which you should understand, because it's exactly what makes this thing. Oh, it's not going to do that. Exactly what makes this thing possible. Okay, that's oscillating slowly. Okay, so we got to be, it's a little bit unbalanced. So in some positions, its potential energy is lower than it is in others. Okay, right now it's past its low point because it's slowing down. It's probably going to start reversing its motion. Maybe a little bit too much friction. Maybe that negative table is on. Okay, anyhow, that beam is going to oscillate. You've observed that. You observed that on the first day of lab. Okay? It's because you have something much like a constant restoring force. I've got some small magnets coming. They're going to help us there for those restoring forces, I hope. Okay? Tiny neodymium magnets. If they're not small enough, I'll take a hammer and make them small. They're pretty fragile. Okay? Okay, now, as soon as you have this, F net equals negative Kx means M A equals negative Kx, which means A equals negative K over M times X, right? The acceleration is proportional to your position, okay? To your displacement from an equilibrium position. Now we've observed that, we've observed pendulums and stuff like that, equilibrium positions, and this thing's back to something close to its equilibrium. I think it's still moving, or is that just my hands? I don't know. Okay. So x double prime is negative k over mx, right? Now, if you're taking differential equations right now, you know how to solve that equation, I think. Okay. You let x equals e to the I theta or whatever. You go from there. Okay. E to the IT, I'm sorry. And you find These all solve this equation, provided omega equals the square root of K over M. Okay? This gives you this picture. If this angle here is equal to the square root of K over M plus Y, and the radius is A, then this is a line where X equals A cosine of omega T plus phi. Why? Because this angle is the square root of K over is okay. This angle is omega T plus phi, omega being the square root of K over M. Okay. So you have this. And you multiply that by A, because for the unit circle, it would just be the cosine. If it's a circle of radius 2, then it have to be 2 cosine, right? You can just scale the circle up or down by factor A, and that is the same thing as the cosine. So here's your cosine. You know, what happens to this line as we move around the circle? Well, it's here. If we move a little further, then the angle is going to be maybe around here, right? So this thing will move over here. And as the angle continues to increase at a constant rate, this thing slows down, comes to rest. Just for an instant, because we keep going around the circle and it comes back. It's its maximum speed here because your speed around the arc is parallel to the x-axis at this point and only this point. So the maximum velocity has to occur here. And then it slows down, comes over here, and it just keeps going. There's simple harmonic motion. And if you want it to go up and down, use the sign, then the same thing can be said about this. Y equals A sine of omega T plus phi. Phi is where you start at T equals 0. And that gets important, but it's there. Well, you plug any of these into this, and it takes you about 2 seconds. If you understand how to do derivatives, you know, I think you got to use a chain rule. Okay, but it's a very simple derivative. Okay, and you're going to verify this. So you're going to verify that any simple harmonic motion is the image of a constant velocity, constant angular velocity motion around a circle projected onto some line. Okay. And if you have that picture, all the equations make perfect sense, other than instead of being something you don't understand, but memorize and hope you plug the right numbers into the right equation when you need it. Okay. And that's what we're trying to achieve in the last 3 weeks of this course, because we've only got 3 more weeks in class. Okay. And we're trying to pull a lot of stuff together. And that's the purpose of the problem set that I thought I posted it for today, but I haven't yet because I really do need to proofread it more carefully than I did the one I posted last week. Okay. Now, it doesn't mean there won't still be errors. It's almost impossible to do a first draft without errors. I'm not that good of a proofreader. All there is to it, I can see what I think I'm going to see instead of what's there. So anyhow, sorry for keeping you over, but this stuff's important. Okay, that's our goal for the rest of the course. And to illuminate everything we've done up to this point.